how many of you have finished the pressure volume lab? Has everybody finished it? Is there anybody in here who hasn't finished it? Raise your hand. Okay, that's what you're going to have time to do tonight here in the lab, to do that. But before I do that, I want to get into the kidney superficially. I'm not going to go too deep. So I'm going to spend probably a half hour lecturing on the renal section. Then we'll call it quits. For those who may have that lab done, you're out of here. I'll see you back here next Monday night. For those of you who need more time with the work loop simulator, we'll be here. Okay? So, one critical point that I want to come back and make to you is that that algorithm for cardiac performance, the kidney is in there, and I already mentioned this to you. The kidney plays a huge role in regulating blood volume, and by definition, because it controls blood volume, it's controlling what? What in our algorithm is it controlling? Stephen?
P.
P.
Yeah.
What in our algorithm?
Oh.
I didn't see P in the algorithm, but I'm sure it's there. Where in the algorithm? The kidney. This unit's, where is it? You look like you knew the answer to that. Should I ask Zane? Should I ask Mr. Ramos? Zimran, what would you say? Short volume, okay, all right. Miss London, what would you say? She says ESV. Megan, what would you say? Philip? What did you say? EDV, you said. You said EDV. I heard him say it very distinctly. He said, and diastolic volume. And where under end-diastolic volume is it there, Philip?
Good question.
Yeah, good question. It's under filling pressure, right? Because under filling pressure is blood volume. And so your kidneys are regulating blood volume, and in so doing, they're regulating cardiac performance. Ms. Javadi, is that the only part of that algorithm that's being affected? I shouldn't ask a closed-ended question. I should be using open-ended questions. So let me follow up. Where in the algorithm? Where else in the algorithm is it active? By the way, I'm not asking this to pick on anybody. I'm asking these questions because these are questions that you should think are fair game for test number 4. By definition, if we affect EDD, what else are we affecting? By definition, stroke volume. But how? What's that? Filling time? No. Remember, one of the things I drew in the algorithm is a line going from end-diastolic volume on over to the Frank-Starling mechanism. And up above that, I wrote preload. So by definition, the filling of the ventricles, the EDV determines the stretch on the sarcomeres. And the sarcomeres are over, under the end systolic volume and under the Frank-Starling mechanism. So by definition, anything that we do that changes blood volume is going to change filling pressure, that's going to affect EDV, and by definition it affects the preload on the heart, and it's going to correspondingly alter where we're at on the ascending limb of the length-tension relationship. That's where you got to be able to go. And that's all in that algorithm. That algorithm, come to find out, there's a lot of physiology there. All right, right, so now turning our attention to the kidneys. So here's a simple summary of what the kidneys do. This seems like a reasonable thing you should know. If somebody asks you what are the various functions of the kidney, you sit there and go, there's 5 of them. As you can see up there, the first one is to regulate the concentrations of ions in the blood. Talk about sodium, potassium, magnesium, chloride. Folks, one of the points I tried to emphasize when we were doing our simulations using metaneuron is that the excitability of cells is dependent upon how far the membrane potential is from threshold. The closer the resting membrane potential is to threshold, the easier it is to stimulate that cell. And we'd say that the cell is more excitable. If the resting membrane potential is very far from threshold, then it's going to be more difficult to excite that cell. And you would say that it's become less excitable. And one of the things that I try to emphasize over and over and over to you is that under resting conditions, the membrane potential is closest to the equilibrium potential for potassium. And that tells you that under resting conditions, that the membrane is most permeable to potassium. And we know that to be a fact because there are these potassium ion channels called leaky potassium ion channels, and they're always open, always. They never close. So anything that you do that affects the concentration of potassium outside the cell, I'm still talking about number 1, is going to affect the excitability of all the cells in the body, including the heart. Go look at your homework assignment. Number 2, the regulation of blood volume. Number 3, the regulation of pH. I don't know if you guys know this or not, but Mr. Body actually won the lottery tonight. That's why I'm asking her all these questions. She won the lottery of physiology question time. Mr. Body, why do we care about pH?
We can denature our proteins.
Say what?
Our proteins can get denatured if our pH is off.
Right, very good. That's exactly right. It said pH is an inverse log scale that describes the concentration of hydrogen ions. Why do we care about that? Because the concentration of hydrogen ions affects the tertiary structure of proteins. We can alter their shapes, and in so doing, we will alter their function. So that's really important. Here's a test question for all of you. How does the body regulate pH? There's one of the answers right there. But what's the other answer? Stephen, what would you tell me? How else does the body regulate pH?
Partial pressure of CO2.
So now we're into our 5-step model. Which phase or which step?
Gas transport. Step 3.
Okay, all right. Ventilation, right? That's where we're really at. We're in step 1, and we're really interested in our ventilation rate because that's how we control CO2, which is how we control pH. So the kidney's not good at acute. It's not great at taking care of acute changes in pH, but the lungs are. So the kidney is more important for chronic, I'm talking about long time periods in terms of pH. There's an endocrine function. I don't think I stressed this, and I should have when I was talking about it. But if you recall, in talking about erythropoiesis, there's a hormone that controls erythropoiesis. And what's the name of that hormone? Erythropoiesis. What's the name of the hormone? Erythropoietin. And erythropoietin is secreted by what? Where does that come from? And here's where I think I failed you guys. Maybe I said this, but let me emphatically say it now. It's secreted by the kidney. The kidney is an O2 sensor, basically. And if you sit there and think about that, I would never, ever, at least initially, sit there and think of the kidney as regulating the production of red blood cells, and in so doing, altering the oxygen carrying capacity of the blood. But when you actually sit there and see what the kidney does, it does a ton of work. It's burning up a lot of ATP. And so when you sit there and think about it in that context, you go, okay, that does kind of make sense that the kidney could play a key role in the regulation of erythropoiesis. So that's one hormone that the kidney produces. So we talk about endocrine function. There's erythropoietin. I'm just going to put EPO up here. One of the things that I have mentioned to you is that when you study physiology, you begin to sit there and say, okay, there's these fundamental stories depending upon the organ system we're talking about. So for instance, if we're talking about the nervous system, and I ask you what's one of the most fundamental stories of neurophysiology, hopefully you'd sit there and say action potentials. Hopefully you would say that. You might say something else, but hopefully in talking about it, you would eventually come to action potentials. If I was talking to you about the respiratory physiology, and I asked you what are one of the most fundamental stories, hopefully you would sit there and say, somewhere in your list, the O2 dissociation curve. That's one of the most fundamental stories. If I was talking to you about skeletal muscle, what would you say is one of the most fundamental stories of skeletal muscle? Copy. What would you say? Okay? But remember, muscles contract. Sean, what would you say?
The sliding filament model. Sliding filament model.
Sliding filament model. Okay, good. I like that. Mia, what would you say? No, you can't say that. Okay. What about that? What would you say, Philip? Okay. All right. Anybody else? Force velocity relationship. What else? The length tension relationship. That's it right there. In skeletal muscle land, the two primary functional properties, contractile properties, are the force velocity relationship and the length tension relationship. So the point I'm getting at is that what's one of the fundamental stories of the kidney as a endocrine function. And here it is right here. Put an asterisk next to this and say, big bold letters, know that's for test number 4. And it's called the renin angiotensin aldosterone story. And these 3 hormones, so these are all 3 different hormones, it's this guy right here that the kidneys secrete. And in so doing, they control blood volume. So blood volume is controlled via the renin angiotensin aldosterone system, and renin plays the central role in that. The other night, we were talking about drugs that can be used to pharmacologically treat the heart. And I asked Jonathan this question about what other classes of drugs are out there besides beta blockers, alpha blockers, calcium channel blockers. And The answer to that was there also are ACE inhibitors. ACE, what does that stand for? Angiotensin. Angiotensin converting enzyme. Well, there's that word right there, angiotensin. This is a huge story and a critical one for regulating blood volume. And then we've got the removal of waste products. All right, so what we're going to do is simple test question. What are 5 basic functions of the kidneys? You're sitting there and saying, we're regulating the concentration of ions in the plasma or electrolytes. We're regulating the concentration of pH, or we're regulating pH. We're regulating blood volume. We're regulating various endocrine types of functions via hormones like erythropoietin and renin, and then we're regulating the waste products within the blood itself. Basically, the kidney is a filtering system that's responsible for maintaining the chemistry of the blood. And what we're going to do is we're going to come along and focus on these basic processes of the nephron, because all of you have learned that the nephron is a basic functional unit of the kidney. And this is really where our story picks up. And in talking about the physiology of the nephron, we will begin to tap into these 5 different functions. So here's a very simple drawing. And these are purely conceptual, right? I mean, these are not anywhere close to being anatomically correct. But we're going to show the flow of blood. So blood is coming through this region, the circulatory system, and up here, we're going to say that this part of our diagram represents the afferent arteriole. I've got this little bend, if you will. And this portion of this representation circulatory system would be the glomerular capillary. Just a point of emphasis is just make sure that you always appreciate that the movement of electrolytes, metabolites, fluid into or out of the capillaries, and gases, by the way, only occurs in capillaries. And in our 5-step model, there are 2 places where we're representing capillaries. That's step number 2, gas exchange, right? The interface between the alveoli and pulmonary capillaries, not pulmonary arteries, not pulmonary veins, but pulmonary capillaries. And then we've got step 4, which is gas exchange at the tissue level. That is exchange of metabolites, ions, fluids, the capillaries of the tissues and the cells of the tissues. So always make sure you understand. Nothing else is being exchanged at the artery, arterial, venule, or vein level. You'll notice that here what I'm trying to do is I'm showing these holes, if you will, in the walls of the glomeruli capillary. These are really important, and these are known as what? Starts with the F, ends with an N. Anybody can tell me? Say it louder, because I got that noise thing going on here. Fenestrations, that's right, very good. What does that word fenestration mean? Hole. Different word for you, window. So these are meant to represent the fenestrations in the capillaries, in the glomeruli capillaries. I'm going to come back and make the next point over and over. Listen to me carefully. Take all the capillaries of the body minus the glomeruli capillaries. So all the capillaries of the body, they're moving about 1.8 liters of blood out of those capillaries on a daily basis. 1.8 liters. The glomeruli capillary is about 180 liters. Sit there and think about this, is that you've got this filter system that is taking 180 liters out of the circulatory system every day. Wow, your blood volume's only 5 liters. How the heck is it doing 180 liters? And here's the answer. Is that of those 180 liters it's taking out, it's putting back 178.2. So sit there and think about that, is that the kidneys are filtering 180 liters of plasma every day and putting back 178.2 in the circulatory system. That's pretty darn impressive. And the ability, the point that I want to make, is the reason that these capillaries are so leaky is because of these guys right here. The capillaries everywhere else in the body don't have fenestrations. All right. And then we have the efferent arteriole down at the bottom here. Associated with the glomeruli capillaries is Bowman's capsule. Coming off Bowman's capsule, we have a very, very important part of the nephron, and this is the proximal tubule. Thank you. Proximal tubule then gives rise to the thick descending limb of the loop of Henle. that gives rise to the thin loop of Henle. The thin loop of Henle then gives rise to the thick ascending loop of Henle. That gives rise to the distal tubule. And the distal tubule then gives rise to the so-called collecting duct. Now up top, if everybody can just look at the board for a moment, up top, I'm going to show a cylinder going across here. And I'm going to describe that as the tubular capillary. So this is the peritubular capillary, so I'm just going to put this little structure like so. I'll mention something more about this in just a second. So this is our peritubular capillary. And if you sit there and look at that word peri, around. So in the real world, this peritubular capillary is wrapped around this tubular network that we're showing you here. I'm just going to represent it as this straight cylinder going across, but you're going to interpret that to really mean that this is in reality really wrapped around the tubular portion of the nephron. Okay, now, there are 4 functions that are being performed by the nephrons. The first function is filtration. And simply stated, that's the plasma being filtered through these fenestrations into Bowman's capsule. So that's our first function. The second function is reabsorption. And here I'm going to put number 2. I'm going to put reabsorb. And under reabsorption proximal tubule, I'm going to put 60% of the filtrate. Well, right off the bat, logic would sit there and tell you that independent of anything else I'm going to say, the proximal tubule is doing the majority of the work for reabsorption, right? Because we're reabsorbing 60% of the filtrate in the proximal tubule. The thick ascending loop of Henle is also responsible for reabsorption. So I'm going to put number 2 again. I'm just going to put reabsorption. And the thick ascending loop of Henle is responsible for approximately 20% reabsorption of the filtrate. Different way of saying it is reabsorbing 20% of the filtrate. The distal tubule is also involved in reabsorption. So here again, I'm going to put 2. And I'm going to write reabsorption. And here I'm going to put approximately 10% of the filtrate. Well, if you're doing the math as we're going along, step number 2, reabsorption. What's step number 1? Filtration. Step number 2, reabsorption. We're going to take what we filtered and put it back into the circulatory system via the peritubular capillary. So we've got 60% plus 20% plus 10%. So far we've accounted for 90% of the filtrate. The collecting duct. Number 2, reabsorption. And here I'm going to put approximately 9% of the filtrate. That takes us to step number 3, or the third function, and that's excretion. Just one thing. What's our excretion rate? That's exactly right. Very good. Anybody? This question for anybody. What's the total volume of filtrate daily? What did I mention? Say louder? 180 liters per day. That's the total filtration the kidneys perform every day. And I also said that of that 180, the kidneys put back how much into the circulatory system? 178.2 actually is what I said. Now, I'm curious. 178.2 divided by 180 is what percent?
99.
It is 99%, which means 1% is lost, and that's right there in our diagram, right? Okay, now, there's 4 functions that the nephrons perform. We're going to focus on the, excuse me, we're going to focus on the 3 that you see up here. Secretion is the 4th one. We're not going to really talk about that. Our focus is on these 3 different functions. And when we come back on Monday night, what we're going to do is we're going to start off talking about what factors determine the filtration rate. Once I'm done describing that, I'm going to tell you a lot more about the proximal tubule and the cells and the membrane transport systems those cells have. Do yourself a big favor. Go review your notes from the beginning of the semester where we talked about membrane transport. That will help you. So we're talking about membrane transport here in the proximal tubule, membrane transport here in the thick ascending loop of Henle, membrane transport over here in the distal tubule, and membrane transport in the collecting duct. As it heads up, once we get done kind of exploring all these things, then we're going to get into the pharmacological manipulation of the kidney in an effort to regulate blood pressure. So let me just come back and say what I said earlier tonight. It said the kidney plays a critical role in regulating cardiac performance. How does it do that? It does it by regulating blood volume. Why do we care about blood volume? Because blood volume determines end-diastolic volume. And in acting on end-diastolic volume, it also determines end-systolic volume via the preload in the Frank-Starling mechanism. So really, really an important story. And because the kidneys can play such an important role in regulating cardiac performance, they're a primary pharmacological target for trying to control blood pressure. So next week, you're going to learn about various drugs that are used to actually treat hypertension, not by acting on the heart, but by acting on the kidney. And there's one known as hydrochlorothiazide. Hydrochlorothiazide is in the top 100 drugs, recognized top 100 most essential drugs. And why? Because of the treatment of hypertension. If you had to guess how many patients that you guys see in your office are using hydrochlorothiazide or HCP?
30, 40%.
Yeah, I mean, it's a frontline drug for treating hypertension. Okay, that's it. For those of you who need to continue working on your pressure volume diagrams, we've got the rest of the night. If you've already completed the work, see you guys next Monday. And the computers are up here. How many people need computers? Raise your hand. How many people need computers?
I thought I did.
Yeah.